So why is spatial interpolation? Spatial interpolation is an approach to create a continuous surface raster from discrete points. An approach of estimate or predict values of variables such as rainfall, elevation, and temperature at any location by using observed or measured values at other location. This is an examples of spatial interpolation. As you can see, there is elevation measurements and interpolated surface. And at the right is ozone monitoring stations and interpolated surface of ozone concentration. UV decelerating and ordinary kriging are the common methods that use of spatial interpolation. So next one is heavy metals. Heavy metals are a group of metallic elements that have a relatively high density and are toxic at low concentration. Some common heavy metals include lead, mercury, cadmium, arsenic, chromium, and nickel, among others. These metals can be naturally present in the Earth's crust, but human activities such as industrial processes, mining, and improper disposal of waste have significantly increased their presence in the environment. Heavy metals can pose serious health and environmental risks when they accumulate in soil, water, and the food chain. Long-term exposure to heavy metals can lead to various health problems, including neurological and developmental issues, organ damage, and an increased risk of cancer. Due to their potential toxicity and environmental impact, strict regulation and measures are in place in many countries to monitor and control the release of heavy metals into the environment to protect human health and ecosystem. E-waste, short for electronic waste, refer to discarded electronic devices that have reached the end of their useful life. These include items such as old computers, smartphones, TVs, printers, and other electronic gadgets. Improper disposal of e-waste can have harmful effects on the environment and human health due to the toxic materials they contain, such as lead, mercury, cadmium, and brominated flame retardants. It's important to recycle e-waste responsibly to minimize its impact on the planet. An e-waste site, also known as an e-waste recycling center or electronic waste disposal facility, is a specialized location where electronic devices and components are collected, processed, and recycled. These sites are designed to handle electronic waste in an environmentally friendly and responsible manner. At e-waste sites, trained professionals disassemble the electronic device, segregated the different components, and recover valuable material for recycling. The process helps to reduce the environmental impact of e-waste and prevent hazardous materials from entering landfill or being improperly disposed of, which can lead to pollution and health hazard. Many countries and regions have regulation and guidelines for the proper handling of electronic waste, and e-waste sites play a crucial role in ensuring compliance with this regulation while promoting sustainable waste management practice.
Soil pollution due to heavy metals at e-waste sites can have severe consequences for the environment, human health, and overall ecological balance. E-waste, which includes discarded electronic devices like computer, mobile phone, and other electronics, often contain toxic heavy metals such as lead, cadmium, mercury, arsenic, and chromium. When these electronic devices are improperly disposed or recycled, heavy metals can leach into the soil and contaminate the surrounding area. Spatial interpolation methods are used to estimate and visualize the extent of pollution and its potential impact. As for environmental impact, heavy metal will cause soil degradation. Heavy metals contaminate the soil, leading to its degradation. This can affect soil fertility and nutrient cycling, potentially leading to reduced agricultural productivity and harm to plant life. Next is groundwater contamination. Heavy metals can percolate through the soil and reach groundwater reserves, leading to the pollution of drinking water sources and affecting aquatic ecosystem. The last one for environmental impact is ecosystem destruction. Soil pollution can disrupt the delicate balance of ecosystems, harming soil-dwelling organisms and impacting the food chain. It may also affect biodiversity and lead to a decline in certain species. As for human health impact, it might cause direct exposure. People living or working near e-waste sites may come into direct contact with contaminated soil, leading to potential health hazards. Next, ingestion. Through agricultural products grown in contaminated soil, heavy metal can enter the food chain and leading to their ingestion by humans. This can cause serious health issues, especially in regions where contaminated crops are consumed regularly. Lastly, inhalation. Dust particles containing heavy metals may be released into the air during various activity at e-waste site. When inhaled, these particles can have adverse respiratory effect. Next, health consequences. The first one will be neurological issues. Heavy metals like lead and mercury can cause neurological damage, especially in children, leading to developmental delays, learning disability, and behavioral problems. Next, carcinogenic effects. Some heavy metals such as arsenics and chromiums, also known as carcinogens, also can increase the risk of cancer in exposure individuals. Organ damage will be also one of the health consequences in heavy metals. Cadmium exposure, for example, can harm the kidney and may lead to kidney dysfunction over time. And the last one is reproductive problems. Certain heavy metals can affect reproductive health, leading to fertility issues and developmental problems in offsprings. Lastly, the long-term effects. Heavy metals are persistent in the environments and their effects can last for generations. Remediation of heavily contaminated sites can be challenging, time-consuming, and expensive. In summary, soil pollution with heavy metals at e-waste sites pose significant risks to the environment, human health, and the well-being of community residing nearby. Proper e-waste management, recycling practicals, and remediation of contaminated sites are essential to mitigate these harmful effects and protect both the environment and public health.
E-waste generated from discarded electronic devices poses a significant environmental threat due to its hazardous component. Through GIS and two powerful geostatistical methods, kriging and inverse distance weighting, we delve into how these techniques help to identify and understand the extent of soil contamination caused by e-waste. Data collection. To apply kriging and inverse distance weighting, you need to collect soil pollution data related to e-waste. This involves sampling soil from different locations within and around disposal sites or areas with e-waste activities. Soil pollution measurement. Measure the concentration of pollutants in the collected soil samples. These pollutants may include heavy metals, the lead, mercury, cadmium, etc., and other hazardous substances commonly found in the e-waste. Data pre-processing. Organize the soil pollution data and associate each sample point with its corresponding pollution concentration value. Environmental application of GIS, such as spatial interpolation, can be used in order to detect the soil pollution. Kriging is a type of spatial interpolation. It starts with the semi-variogram calculation. Compute the semi-variogram for the soil pollution data. The semi-variogram describes the spatial autocoloration of the pollution values, indicating how they vary with distance and direction. Semi-variogram model fitting. Select an appropriate semi-variogram model that fits the data well. Kriging interpolation. Applying kriging using the fitted semi-variogram model to predict pollution concentration at unsampled locations. The method will consider the spatial relationship between sample points and assign weights to neighbor points based on their similarity and distance to the target location. Next, inverse distance weighting. Inverse distance weighting interpolation. Using inverse distance weighting to estimate pollution concentration at unsampled locations. Inverse distance weighting considers the inverse of the distances between the sample points and the target location, giving more weight to points closer to the target location. Pollution concentration maps. The interpolated pollution values obtained from both kriging and inverse distance weighting can be used to create pollution concentration maps. These maps visually represent the spatial distribution of e-waste-related pollutant in the study area. Analysis and decision making. Analyze the pollution concentration maps to identify hotspots or areas with higher pollution levels. This information can guide environmental management and remediation efforts, helping authorities to prioritize contaminated areas for cleanup and remediation activities.
Based on the study conducted on soil pollution, heavy metals using the spatial interpolation method at an e-waste site. The conclusion is that the soil at the e-waste site is significantly contaminated with heavy metals. The spatial interpolation method revealed the presence of high concentration of heavy metals throughout the site, posing potential environmental and health risks. Urgent remediation and proper waste management strategies are necessary to mitigate the pollution and safeguard the surrounding environment and communities from further harm.